There is a common uh, feature between these photos, or they express a relationship between a quantity with another. For in the table we have years with populations. We can read here sport cars with colors. So also here there is a scatter plot, and the last one is a curve. Okay, expressing the variation of a quantity y with respect to a quantity x. Not all there isn't necessarily one method to study all this kind of information. In our study, we will focus with the last one, the one where the relationship is expressed by a formula. And this kind of relationship we are interested with is a function. We want to study a relationship given by a formula linking two variables, an independent variable x, okay, independent variable, okay, with a dependent variable y. So this is the dependent variable. Okay. Okay. Now, so this is the purpose of the course: is how to know completely the function, and at the end be able to graph it and express express many information from the graphing or during the study of the function. So our purpose is to develop tools to deal with this kind of relationship. So the first thing we will focus on, the first thing is we need to know the function. So we need to know where is it defined. This is what we call the domain. Okay. Okay. So the domain, sorry here. Okay. So independent variable. So as I said, we are interested in first knowing where our function is defined. Okay, so what is the domain? Yes, what is this domain? So this domain, the domain is where my formula is has meaning. When I can substitute a value for x and can be able to compute fx. So what I will call the domain of f and write it like that, denoted it like that. Usually we use the index f to express which function we are dealing with. So the domain will be the set of all possible values. The values are real numbers. We work, so here clearly also we focus with functions, real functions defined on R. Okay, so that fx, when I compute it, means that I will get a number. Okay, a real number, well defined, etc. Okay, so a simple example here. Let's do an example here. An example: if you have, for example, fx equal 1 over x, or like the function defined graphed here is the domain, the function is x minus 1. Okay, so clearly here all possible values are all real numbers, only one we must avoid, one, because the denominator takes the value 0. So necessarily my domain f will be I will say all the real numbers minus the point 1, the value 1. Okay, if you use if you use the real line like that, okay, sorry. Okay. Okay. So here is my line here. Let's move it here just to show you something. Well, so if let's continue with the green color. So here is my line, real number. Here is 0, and here is 1, for example, 1. Okay, there is another way to express domain instead of sets like that or descriptions like this one. Here we can use intervals notations. So the only value that is causing problem is the value 1. Okay, the value 1 that must be avoided. The remaining values can be considered included in the set. So finally, my domain, I can rewrite it differently using interval notation. So it's minus infinity up to 1. Open brackets, keep it open so that I express that I'm not including 1. Then use the symbol union, and then again open the brackets means that I exclude the value 1, number 1, and go up to plus infinity. Minus infinity and plus infinity are not numbers, so always it will be always open like that. They are just symbols that shows that you are going infinitely large numbers or infinitely negative large numbers. Okay, so this is my domain for this function. Okay, let's take another example. Oh, it's enough for moments. Another set, important set. So if you look here at in the graph, if you look yes, if you look at the graph here, let's make it bigger. No, sorry. Okay, okay. So if I yes, if you look at the graph here, so 1 here, the value 1 is excluded. Okay. Um, let's take now consider another set, important set for functions that it helps to know the function, gives information on the function. So it's the set called the range. Range of f is the all possible values taken, the y's taken by f. So it's the y's. So the y's are that we can write them y of n fx. Okay, with x in not any real number, but in the domain when it is possible to take to express fx. Okay, so like that, this is the range. So if you look at our function here for this example, okay, so we will have the range of f, okay, that this time also, so the only value that is not included is 0, okay, is 0. So we see that any values here is described of y, only 0, there is no x, so that y equal 1 over x minus 1. So finally the range will be minus 1 infinity to 0 union 0 plus infinity. And we can see it through the calculation. If you solve the equation, when you solve y equal 1 over x minus 1, okay, to look for if whether we have an x, so that we have this equality. Okay, this is our purpose. Can I find an x so that 1 over x minus 1 is an fx? That means y. So when you solve this equation like that, so the unknown y is given, and x is the unknown, and x is the unknown, we are looking for it. Okay. Okay, let's move. Yes. So if you try to solve this equation, look what happens. Okay, so I will say y equal 1 over x minus 1. So here x must be different from 1 from the beginning, otherwise this equality doesn't make sense, it's not defined. So I can then write y times x minus 1. So the purpose is to isolate x, find an x, okay, equal 1. Multiply both sides, okay, equality with x different from 1. So we are looking for x. So let's isolate x. X times y minus y equal 1 with x different from 1. And here, so uh, move all the terms to the other side. So you will have xy equal y plus 1 with x different from 1. At this level, pay attention. You need to find x. To find x, so you need to divide by y. To divide by y, you must be sure that your y cannot be 0. So this you can keep the equivalence, but you must add x equal y plus 1 over y with y different from 0. Okay, x different from 1. Okay, so that's, and at this level we see that the value 0 must be avoided. It's otherwise, if y equals 0, okay, if y equals 0, we will have x times 0 equal 0 plus 1, okay, which is impossible, because you will have then 0 equal 1, okay, impossible, okay, there is no solution. So here it is. The range then must, and you can see it through, if you look back, look here at your graph, you see that 0 cannot be reached by any x. Okay, so these two sets so are important. Okay, that is let's do another example, maybe, or let's continue with another set. Okay, so the other set, okay, the other set is the graph set. Okay, the graph. Okay. Okay, so the graph, as you know already, you met already graph of function. So the graph, the curve you are looking at in this figure, is the graph of our function. So it's all the points in the plane that have coordinate x, fx. Okay, we regroup all the possible x's where f is defined and the y corresponding as this x, and we plot the points, and you will gather all those points, and which forms the set graph. Okay, so the graph is a subset of the plane of R2. Okay, so the graph by definition, let's write it bigger. So the graph of function, the graph of f will be the set of points x, fx. Okay, when your x describe all the domain. Okay, so it's included in R2, which is the plane. Okay, great. Okay. Okay, so yes, we have this. So let's do another example. In this, yes, another example for, here it is. So I'm considering this function, new function, square root of 1 minus x2. Okay, for a moment, we don't have enough tools to graph such function. We didn't study this, but this particular function, you will see you can graph it because you will see why. Okay, so first let's look at the domain. The first thing you must be curious about it is always to check your domain. Okay, so the domain, okay, domain of f. So here I need to gather all the real numbers so that what? Here I have a square root, so I need to be sure that inside the square root the quantity is positive. The square root is defined only for positive numbers, so I need to be sure that what is inside must be positive or equal 0. And here now I have an inequality, second degree inequality. So you know how to do it. Let's do it quickly here. Okay, so just like a review, usually to solve inequalities, we factor our um, term in simple terms that you know how to solve, study a sign of quantity. So usually the idea is to have terms that you know how to deal with. For example, uh, to know the sign of the product, if I know the sign of each term, I can deduce the sign of the product. So a practical way to do that is to make a table of signs. So here is x. So I have the term 1 plus x. I write the term 1 minus x. Then the product 1 minus x2. Okay. So then I do the first work. I ask myself, when do I have 1 plus x positive? So this quantity, this will happen if my x is greater than minus 1. So let's erase this part and write it just close to it. Okay, so here. So it will happen if and only if x is greater than minus 1. So minus 1 is a value that is important. It appears here. And let's deal with the other term. 1 minus x will be positive if and only if 1 is greater than x, which can I read as x less than 1. So 1 also is a value, an important value that appears. So now let's put the signs. This quantity will be positive for x greater than minus 1. X greater than minus 1, I am here. So I will have a sign, positive sign here. It will be 0 at minus 1, yes, and negative elsewhere. For 1 minus x is positive for x less than 1. Here is the x is less than 1. I read them here. For this factor, it will be then positive here and negative here, equal 0 at 1. Now, what about the product? The product is 0 if one of the factors is 0. So it will be 0 here, okay, and 0 here. Now, if my first factor is negative and the second positive, then the product will be negative. If the first is positive, the second positive, it will be positive. Positive and negative will be negative. So now I see clearly that my product will be positive if and only if I have x between minus 1 and 1, including 0, it's not important, okay? So the answer is, the domain is, I can write it here, minus 1 and 1. Okay, what about now the graph? Let's do the graph. The set graph. Now the graph of f will be the set of x fx, okay, or the xy with your y equivalent fx, which is square root of 1 minus x2, and your x is between minus 1, 1. We know it now, the domain. Okay, so we said we don't know how to study such functions, but you will see it's a particular function. So remind the technique we are going to use here each time you have a square root of something like that. So let's look at this relationship, 1 minus x2. Okay, with x between minus 1 and 1. I can say that this is equivalent to, I can square y squared, take the square both sides. So I will get 1 minus x2, but keeping the information that x is between minus 1 and 1, and what else? And that y is positive. Okay, otherwise here my y is positive, so when I take the squares, I need to keep the information, this information. Otherwise, it is hidden with a square. Even y negative can satisfy the equality, but not this one. Okay. Here it is. Now let's one more line, and you will identify your set. Move x2, and we will get this equality with x between minus 1, 1 and y positive. So now, if you, without looking at the second line, the first equation is the equation of the unit circle. Okay, this is the unit circle. Okay, circle. Yes, I think it's y. The unit circle. Okay, and the restriction y positive means that I need to consider only the upper half of the circle. Okay, so the graph, my graph finally will be something like that. Okay, so here it is. If I have unit 1 here, unit 1 here, okay, my graph will be something like that. Okay. Okay, so this is the graph of f. It has the equation y square root of 1 minus x2. Great. Okay. Now, let's see another idea now. Let's look at this graphing. Okay.